It's about a case study in implementation space exploration, but it's not about space, but it's about the implementation space. It means that we want to analyze different versions of our algorithm. So, first I will give a short introduction to depth of field and the algorithm itself. After that, I will move forward to the C-Mera and the feature system. And in the end, I will show you how our actual implementation works and our results. So, let's have a look at the depth of field and the algorithm itself. What we want to do is to introduce a sort of filter to simulate or to introduce the depth of field effect. It means that objects might appear blurred or not in focus. But when we use or when we generate images artificially, so we don't have this effect from the algorithm itself, so we have to introduce it afterwards. And why do we want to do so? Because we want to simulate cameras or for statistical reasons, for example.
Excuse me, is the microphone turned on?
You don't hear me? So, better? Okay. Now let's have a look. When we use a normal camera, we have some sort of optical system. That means that we normally have a lens, and then in a specific distance we have some point that we want to capture. Then the lens focuses one point of our object into one single point of on our image plane or our sensor plane. It means when we move the object, then it appears that our resulting image might get blurred. That means that this area, the circle of confusion, is then mapped into one single point of our sensor. But when we generate images artificially, we don't have that kind of optical system. But we also want to use or introduce some sort of effect. So then we might add the same effect by blurring the pixel or mixing them with the neighborhood pixels, depending on the distance of the captured image, captured point. So when doing this right, we end up with such images. As you can see, objects far away are rather blurry, whereas images or objects near to the camera are sharp. And the effect increases depending on the distance, as you can see here in the rigging. The focus distance might be around here at the side. So we want to apply this effect efficiently and fast, so we want to use graphics card. And to do so, we have to use the algorithm a specific way to make it easier for the graphics card to access the data and to process the data. And to do so, we divide the input image to single tiles, and then we process every tile individually. And that's the way how we do it. We introduce a list per tile, and then we sort every pixel inside one tile into the list. Then we check the surrounding area and add the pixels with a circle of confusion that might overlap with our tile. That means when we filled our list, we only have to process per tile only the list. Then we simply loop for every pixel or iterate through the list and then mix them together, depending on the circle of confusion. So that's the essential way. And for the rest of my presentation, I will focus on the accumulation loop itself. It means that how we accumulate this effect or how we accumulate the list efficiently. So when we're doing so, we might test different versions of our algorithm. For example, we can try different accumulation orders. That means that we can accumulate our list from front to back or back to front. Or we can actually, or alternatively, use different node types. In the list, we have additionally to the color, we also store the image position, the pixel position for X and Y, and the circle of confusion. When we use different node types, we can actually add information, for example, the transparency or the alpha value to reuse it later. Then what I've not told yet, we iterate through the list not pixel per pixel, but we load them chunk-wise. And we tried different sizes of the chunks to reduce the latency for the global memory access. Then we have tested early out, so we can, when we iterate over the image, then we can try to, per pixel, try to exit the loop, or exit the loop after a chunk is processed. The next and my favorite part was how do we handle the residual chunk? That means that the last element in our list might be not filled completely. But you will see in the later, I will show more details on this part. Additionally, we tested different distance types. It might look silly because we simply tested different types, for example, integer type and a float type for the computation. But because we use graphics cards, they are optimized for float types. It has a rather big impact on our performance. So, and then we tested the different types of alpha fetching. One possibility is to compute the alpha on the fly while processing the list. And the other possibility is to load it from the node when we use a node type where we can store the element. And then two different small improvements. We tested to apply the read-only cache while processing the list and to explicitly load elements in a local register. So, what we want to do, what we wanted to show. We wanted to test all possible combinations of the previously shown variations. Then we wanted to find new optimizations. In fact, the latest we tested the distance type rather lately. Okay. So, and we wanted to, of course, identify the best solution concerning the performance. And the most important part, we wanted to use one general implementation. That means that we didn't want to copy-paste our code and then modify it by hand. We want to use one single implementation and then instantiate different versions of our code. And of course, we want to do it with as less effort as possible. And to do so, we used C-Mera in our feature system that I will give you a short review now. So C-Mera, Kai already talked about the system, but I will repeat some small parts. For example, C-Mera is a source-to-source compiler which transforms specific S expressions to a C-style result. And while processing our S expressions, we can use completely Lisp itself and Common Lisp-macros, and of course, the Common Lisp object system for the pre-processing pass. And that's the way, or that's what we feed C-Mera with. It's the input code. And essentially, this is our accumulation loop. But in this case, we don't use the chunk-wise load, but we load every single element. So how does it work? So we simply step through the loop, then we load the element, then we load the distance and compute the distance, and then we load the circle of confusion, then we test if we are inside the circle of confusion, then we compute the transparency of the pixel, and then we blend them together and store the result image. And that's what we get that's the resulting code in C style. And now we want to introduce our variations for this code. So the first idea is to try some sort of macro and to introduce these variations. And one possibility is, for example, this one, where we tried to introduce the early out variation. And the idea behind this is that we simply pass in the body, and depending on the target, we get different implementations. For example, when we use the blockwise early out, then we get the body itself and introduce an if statement with a break. But of course, that's not really nice to use because we have 8 different variations. And when we try to combine them, they depend on each other, and it's not really nice to handle. So we use our feature system. And feature system are in fact like our macros, or like macros, but they have an additional feature. And that's that we can implement, for one feature, we can implement different implementations depending on the targets. And then we get different result codes. The idea, that's the way we set up our features. It's essentially the same how we used the macro previously shown, but at this implementation we don't need the boilerplate code for the condition in the beginning. So we simply define the targets, then we define the feature, and then we implement every single instance of the feature for every target. And in that way, we can then apply the features and instantiate different versions. The idea is that we can simply introduce one simple configuration into a global here, and then the following features will then expand into the corresponding code. So, what's the next step? The next step is then we introduce different layers and combine features with features, and then we can nest them and we get our resulting code. Now we have different features with different implementation, with different expansions. So we use different targets. But in fact, our targets can be derived from each other. And the final step is that to include or derive one single target from every target and use it globally in one point. So let's move on to our implementation, and we'll see how we use this single point for instantiation. And that's the same loop as previously shown, but now spiced with our features. And this point and this code fragment can expand to over 300 different versions depending on the global configuration. And now we will see how we manage or handle the residual block, specifically set with the loop over blocks feature and the process blocks feature. We'll have a more detailed look at that. So we have two possibilities to process the last block. One possibility is to loop over every block. We process the list, then we loop the list for every block, and then we check if we are in the last block and set the upper limit for the inner loop accordingly. The alternative for this approach is that we split the last element and process it individually in the last instance. So the idea now is that we don't have to check in each iteration over the blocks, so we can simply set a fixed upper limit for our loops. And that's the way how we implemented them with our feature system. That's the simple one. We just loop over the blocks. Then we, as you can see, we include the last iteration. It's a smaller equal. And then we pass in the body. And then for each individual block, process the blocks. And then we check if we are in the last iteration and set the upper limit accordingly. The alternative for this approach is that we, as already said, is we split our implementation to two elements. And now it's the idea that here we loop over the blocks and process them in the list, but now we skip the last iteration and process the last element individually. And as you can see, we duplicate the body in both parts. So we use only one single implementation of the body and then introduce additional targets in our global target configuration. So we pass in a configuration and then we extend it with a full block target. And in the same way we extend in the lower part, we extend it with the peel block target. And then the process blocks are much simpler because we now don't have to check for every iteration, but simply set the upper limit fixed. And all in all, this configuration or this our system expanded in, as I already said, to 320 versions, and we tested them on 3 different graphics cards, and that's the result. So the best implementation we found was this one, highlighted in green. It's the best implementation for the Maxwell architecture. And in blue, highlighted in blue, is the best implementation for the Kepler architecture, for the Titan. As you can see, the results are normalized. So the fastest implementation has no bar at all, and the slowest one will reach the top. So, as I already said in the beginning, the very interesting part was our float and integer distance type, and the distance types are shown here. The red one is the integer type. As you can see, these 2 blocks, and the float one is these 2 blocks. The interesting part is that also that the Titan architecture is not always, does not use the same implementation, or is not as efficient with the same implementation as the Maxwell architecture. So you can see that it's better to, for the alpha fetching, it's better to load, to compute the alpha value on the fly for the Kepler architecture, but to load the value for the Maxwell architecture. As you can see, too, is that what's quite interesting, that the pattern of the Maxwell architectures, these both are quite similar, but they perform in different ranges. Okay, the input code is about 275 lines of code, and the result code is about over 16,000 lines of code, with 320 versions of the resulting of the actual accumulation loop. So, we're reaching the end. We managed one implementation without redundancy, with one single point where we implemented the complete system. Then all modifications have now global effect because we only have one single point of implementation. That also means that we can guarantee coherent code. It means when we would use a copy-paste method, for example, and then copy our implementation, then try to introduce additional features per hand, we can end up with errors. That cannot happen with this approach. And then we are able to unfold, examine, and maintain all versions with one single implementation. And what's also interesting is that we can inspect individual instances. We are not stuck with this single implementation. We can expand them and inspect every individual instance. And of course, we can try to introduce new variants incrementally, step by step. And of course, the idea was to find and identify unexpected outcomes. Thank you for your attention.
Thank you very much. Any questions? Yes. Was that predictable? I mean, that second last chart.
This one.
You as a graphics expert looking at all this chart, did you predict that kind of behavior, or did you survive?
The distance type, it was not surprising that the float part was faster than the integer type. But it was not that expected. It would be, this impact is not, it was not expected.
Do you factor in resulting image quality as well? Like how do you deal with like one approach, higher sampling might result in
I don't.
Looks worse than the resulting image.
No, the results were, every result was equal. There was no difference at all. If we would have different result images, then there would be something wrong inside our implementation.
Okay, cool. Yes.
I assume this results from the background parameters of Friedrich-Alexander, which are pretty perfect. As an aesthetic consideration, most camera lenses tend to produce background blur that's distinctive. And so artificially create a depth of field can look too perfect. Talk about introducing aberrations.
it looks not that perfect when we, as good as when we use or simulate real lenses. Because you don't have the transparency effect, you can't see behind objects. That's still missing. So when you know what you see that it's not correct.
Other questions? Yes.
What if you simulate what I do, which is put my finger over the lens?
Any other questions? Well, we're a bit early, but we might as well have some tea. Thank you very much.